If you were a dark wizard and you were trying to hide what spells you were writing down, how would you do it in my system? For those that don't know me, I'm the Gorilla of Destiny. Look, it even says there, my friends bought me this, it's amazing. And I made a system for how to write down spells. And now I've made a system for encrypting spells. And to give an idea of how powerful it is, I'm currently running the code-breaking software. We'll see if it even finishes 1% in the time it takes me to record this video. And it's going to be starting with a 9-minute head start. So how do we encrypt a spell in a way that we can read it but no one else can? Well, first let's talk about how we read it normally. This here is our starting point. To get the first of the 6 binary numbers we need that describe every spell, we simply count round from this starting point going around, and anytime there's a line that connects one point to the next one along, we write a 1. If there isn't one, we write 0. So in this case, we've got 1, 2, 3, 4, 5, 6, 7, 8 zeros, followed by 1, 0, 0, 1, 1. And that gives us the code that's for the level of the spell. Then to get the next code along, we just look, but instead of going to the next point along, we're looking for a line that connects 2 points along. So in this case, it's all zeros until we get to these ones where we have a 1 and a 1. And so on and so on. So this is how we read. Now, this is all dependent on us knowing the order of the dots. The starting point itself doesn't matter because I chose the binary codes to be rotationally asymmetric. Basically, that means if we started counting from here, we would get the same pattern as if we started counting from here. It'd just be shifted over a bit. But everyone knows that as we're going clockwise, we go 1 through to 13. But what if instead we changed the order of the dots? And only we had the key telling us which dot is in which place. That's where the encryption comes in. Now, it took me a while to get some of the maths working. I might go into this at some point, but this is all we need to focus on now. We're just going to swap the dots around, but keep the connections if they exist. So here we're connecting 1 and 9 with this big line here. If we were to move 1 down here and 9, down here next to it, we would still have that connecting line, basically. But what that means is that figuring out these K values is going to be totally wrong. Because the number of dots that are being skipped is now going to be different because we're shifting all the dots around. And so if someone doesn't know the order that you've decided to put your dots in, they basically have to check, and I'm not good at code breaking, but as far as I'm aware, they have to check every possible combination of order of dots. How many combinations is that? That is 13 factorial. That means 1 times 2 times 3 times 4 all the way up to times 13. Or in other words, 6,227,020,800 different combinations. And so in the time it's taken me to record this video, it's been going now for 8 minutes since I started recording, but now, about 15 minutes, it hasn't even done 1%. Anyway, I might talk about some of this in another video. Have a lovely day. Okay, bye.